In theory, determining your location on Earth is an exercise in clean, elegant geometry. If you know how far away 4 satellites are, you can draw 4 spheres, and they perfectly intersect at a single point to pinpoint your position. We calculate distance using this straightforward equation. Distance equals the speed of light multiplied by time. The math assumes c is an absolute constant, but that only exists if the signal travels through a pure, empty vacuum. Earth is wrapped in a thick atmosphere. When radio waves hit these charged particles, the signal physically slows down. Because of this delay, the calculated distance is inflated, causing those precise geometric spheres to stretch, warp, and entirely miss their target. If you rely on a broken speed constant, your phone will calculate that the satellite is hundreds of meters further away than its true position, rendering your ground coordinates entirely useless. The core engineering challenge of GPS is figuring out how to force this imperfect physical environment to yield mathematically perfect location data. Basic arithmetic isn't enough to solve this. Finding true positioning requires breaking the radio signal down to its physical components and dynamically repairing the damage it suffers during its journey through the atmosphere. The first obstacle to clear is the sheer volume of data. If every satellite in orbit simply broadcasted a literal clock timestamp, the overlapping signals would crash into each other, leaving your receiver with impenetrable static. To solve this, engineers built the system on a protocol called Code Division Multiple Access, or CDMA. CDMA allows every single satellite in the GPS constellation to broadcast its data on the exact same main radio frequency. Instead of relying on separate channels, the system assigns a unique identifier to each satellite, called a pseudo-random noise, or PRN code. By stripping away overlapping frequencies, we isolate a structured sequence of binary ones and zeros. While seemingly chaotic, this PRN code is a deliberate, highly predictable mathematical pattern generated by the satellite. True static has no internal logic. The PRN code is a digital fingerprint designed specifically to be recognizable by the hardware on the ground. Your phone already has a directory of these unique codes. By listening to the main frequency and hunting for these specific mathematical patterns, the receiver can pluck one specific satellite's transmission directly out of the ambient noise. The processor inside your device does this isolation routine simultaneously for 4, 8, or even 12 different satellites, all while listening to a single, crowded radio frequency. Without this underlying PRN architecture, the GPS frequency would be a deafening roar. Because of it, we have a readable, structured spatial map. But if the satellite is transmitting a complex code rather than a simple clock timestamp, how does the receiver actually extract the precise transit time? It starts by generating its own perfect, pristine replica of that satellite's specific PRN code internally. To find the transit time, the receiver uses a process called cross-correlation. It takes the incoming radio signal from space on top and slides its internal replica backward and forward along an axis of time. It continues sliding until the ones and zeros perfectly interlock. The exact physical time shift the receiver had to apply to its own replica to achieve that lock is exactly equal to the signal's transit time from orbit. Transit time isn't a number read off a screen. It is a deduced measurement, derived from the physical alignment of complex mathematical patterns. The fast-moving PRN code is doing the heavy lifting for the timing, but it acts as a carrier layer. Superimposed on top is a much slower, low bitrate data stream called the navigation message. This wave contains 2 distinct packets, a rough, low-resolution almanac of the constellation, and a razor-sharp, precise ephemeris. The ephemeris provides the exact meter-level orbital position of the specific satellite transmitting the signal. Your receiver cannot calculate its location without knowing exactly where that satellite is in 3-dimensional space. Because this space transmission is so slow, running at just 50 bits per second, downloading the full ephemeris directly from the satellite used to take a legacy GPS device 12.5 minutes to achieve a lock.
Modern receivers utilize assisted GPS, or a-GPS, to bypass the space link. By pulling the exact same ephemeris data through terrestrial cellular and Wi-Fi networks, modern phones condense a 12-minute orbital download into a millisecond operation. With the orbital geometry locked in, we have to deal with the physical drag of the atmosphere. specifically the upper layer, known as the ionosphere. The ionosphere is a dense blanket of free electrons, charged and rendered highly volatile by incoming solar radiation. As incoming electromagnetic radio waves enter this matrix, these charged particles exert a physical drag effect, delaying the signal before it reaches the ground. To solve for this unpredictable delay, modern high-end receivers rely on dual-frequency tracking. Instead of listening to one signal, the receiver simultaneously tracks the legacy L1 frequency band and a newer, stronger L5 band, both transmitted from the exact same satellite. Because the ionosphere drags on different frequencies by different amounts, the L1 and L5 waves arrive at slightly different times. By subtracting one timestamp from the other, the receiver can mathematically calculate the exact thickness of the ionosphere at that very second. By measuring the delay across two bands, engineers use the atmospheric error itself to calculate the cure, neutralizing the physical distortion. Even with perfect upper atmospheric math, the signal still has to survive the chaotic, reflective environment of a modern city at ground level. In an urban canyon, you encounter the multipath error. A radio signal will often physically bounce off a solid structure, like a glass skyscraper, before reaching your phone. The math assumes a straight path, as shown by the red line. But because the signal took a V-shaped detour, the total travel time is artificially lengthened. Your phone processes the delayed transit time and calculates that the satellite is much further away than it actually is, causing your location on the map to jump. We also have to account for the dilution of precision, or DOP, which relies entirely on the physical arrangement of the satellites in the sky above you. Comparing these two models, we see the impact of geometry. When satellites are tightly clustered together, their intersecting spheres create a large, stretched, imprecise zone. When the satellites are widely spread across the horizon, the intersecting spheres cut razor-sharp lines, creating a pinpoint location. If poor local geometry or an urban environment corrupts the raw data entering the receiver, all the atmospheric corrections in the world cannot save the final calculation. Standard PRN code matching can confidently put you within 1 to 3 meters of your true position, but professional surveying equipment and autonomous vehicles demand millimeter-level accuracy. To reach that scale, we hit the physical limit of the digital PRN code itself. A single 1 or 0 in that sequence is physically about 300 meters long in space. You cannot measure millimeters using a 300-meter ruler. Achieving extreme precision requires a different approach entirely, ignoring the digital payload and focusing strictly on the raw physics of the wave. This is carrier phase tracking. Professional receivers dive completely past the 300-meter digital code blocks to lock on to the fundamental underlying analog psi wave that carries the signal. This underlying L1 carrier wave operates on an incredibly tight scale. One complete cycle of this wave measures just 19 centimeters from peak to peak. But measuring a 19-centimeter wave is still useless if residual, uncorrected atmospheric errors shifted out of its true physical position on the ground grid. To solve this final vulnerability, professionals use real-time kinematic, or RTK, networks. They rely on fixed, stationary ground bases that calculate exact, localized atmospheric delays. They broadcast these corrections directly to the moving receiver, instantly shifting that 19-centimeter wave into perfect millimeter-precise alignment. True millimeter precision isn't achieved by building better clocks. It is achieved by discarding digital approximations and anchoring our equipment to the dynamically corrected physical waves falling from orbit.